And so now I'd like to turn to our next session, which is kind of generically called LiDAR use in the Maya region. And so we're going to go from the Amazon to the Maya region, but to my way of thinking, I see a lot of parallels in what's happening in the Amazon and Amazonian prehistory, and what happened in what's still happening in the Maya region, really, but what happened, you know, a few decades ago with this sort of rethinking of Maya landscapes, et cetera. And then it kind of happened again with LiDAR. And so, you know, I'm very honored to present a whole slew of people who have sort of been instrumental in reformulating Maya prehistory using LiDAR. And so, of course, first we have Arlen, Diane, and Adrian Chase, who are joining us from disparate areas, I think, unless maybe Adrian's there in California too, I guess, I don't know.
Yep, temporarily.
And then we have Takeshi Inomata, who's joining us from Arizona. And so the Chases, of course, are going to talk about change perspectives on the ancient Maya past, which, to be honest, they largely engineered. They were the first ones to really use LiDAR in a big way at Caracol. And certainly they're the reason that we started using LiDAR at Angamuco in Mexico, because of all the press and attention that they got from their project. We saw that and we were like, let's try that. And then it fundamentally changed the course of my career, I guess. And then we'll have Takeshi Inomata, archaeological investigation through high resolution and low resolution LiDAR in Mexico. And Takeshi has pioneered the use of combining, doing data fusion really on disparate kinds of LiDAR records. Hopefully Keith Prufer appears. He seems to be missing. And Amy, I don't know if maybe oh, here he is. Oh, he just appeared. Good. Okay, never mind. So Keith is going to talk about LiDAR archaeology and human adaptations in the neotropics. Keith was also an early adopter of LiDAR, I would say. And then finally, we have a talk from Amy Thompson and Gary Feinman, integrative perspectives on multiscalar classic Maya inequality. There's Gary. And as many of you probably don't know, Gary was my advisor, and he's probably still disappointed with my work ethic, I'm sure. So with that, we have an hour. Everybody has 15 minutes. We might be able to eke out a few more minutes for questions at the end, but probably not. The organizers are telling me. So everybody has roughly 15 minutes to give their paper and address any questions. And I want to thank everybody again for agreeing to come and speak at the Congress. We're very excited to have you. And without further ado, I guess I'll turn it over to Arlen, Diane, and Adrian.
All right. I wanted to first, I assume everybody can see Kana on the screen. I want to first thank Chris for inviting us to be part of this Earth Archive Congress. I also want to talk about LiDAR from the standpoint of Caracol, which is where we have been working for now 37 years, with the one exception of this last year during COVID. And what I wanted to also say, gotta get this going here, is we had lots of issues in terms of getting an understanding of archaeology at Caracol, largely because we were miles from nowhere in a forest, and the forest literally covered everything that we could see. And this is pointed out early on by Alfred Kidder in the 1930s when they were doing flame flights over the peninsula, that there's difficulty in interpreting the classic period Maya. We started work at Caracol in 1983 when the site consisted of 78 structures. We mapped with a transit under the jungle canopy for some 20 years. We succeeded in getting 23 square kilometers, but we were no closer to actually knowing what the site looked like as a whole after those 20 years than we did before. So we started looking for alternative technologies. And one of the things that we identified as early as 2005 was the potential for LiDAR. It took us 5 submissions to NASA to finally land the grant that, for LiDAR, for block mapping LiDAR. In December of 2007, it was carried out by the National Center for Airborne Laser Mapping, but they couldn't do it to 2009 because they were, in fact, changing their equipment. And I think the change of equipment actually benefited us on those 2009 flights, which took 3 days to record 10 times the amount of space that it had taken us 20 years to record. This was reported in the New York Times in 2010. We did an article in the Archaeology magazine in 2010. Most of our colleagues complained about the cost of LiDAR at that time. We tried to submit to science, and science decided it wasn't really ready for my archaeology. They finally came around to that with the Canuto article in 2018. However, in working with Chris, we all submitted an article of the Proceedings of the National Academy of Sciences, which we called Geospatial Revolution in Mesoamerican Archaeology. And in fact, we are all now credited for coining the term Geospatial Revolution and for helping Mesoamerican archaeology catch up with the field that had started in 2005. In 2013, we returned to Belize with a consortium of all of the archaeologists working in Western Belize and got another 1,050 square kilometers of LiDAR, which actually finally enabled us to start to get some sense of what Caracol, the city, looked like. So there you're looking at our 2003 block map of 23 square kilometers laid on what we now recognize to be the limits for the urban city of Caracol. And you can see how large it is in terms of the Belize map to the right. Now, what LiDAR has successfully done for us in terms of Mayan archaeology is it has provided a large-scale spatial context that we did not have before. And the LiDAR data can be joined with archaeology and epigraphy to make new interpretations. So how LiDAR has impacted us since 2009 is it's helped us look at the early development of Maya civilization. It helped us look at intensive anthropogenic landscapes that the Maya built. We can look at differential infrastructure throughout the Maya area. We can look at defensive earthworks. We can look at the size of classic Maya cities, large-scale agricultural intensification, and definitely updated perspectives on ancient Maya society. So LiDAR has really revolutionized a lot of what we think in terms of the Maya. Just to reiterate, when we started at Caracol, in 1983, we had 78 structures. Today, those 78 structures fit in the middle of the site in the letter C. So just give you a sense of how the scale has changed overall. One of the other things that LiDAR has changed is how we do Maya maps. Rather than just line drawings of where architecture is, we can now actually see how these structures fit onto the landscape. We can see the topography. We can see other features such as terraces that we tend not to map. LiDAR also gives us great detail. Remember, these are all points. Change the lighting, you see different things, but it allows us to interpret features that are on the ground, structures, groups, and even small collapsed tombs, such as the one we see there. We can look at how the landscape is integrated in terms of LiDAR. So this is a 500 meter by 500 meter area showing you public architecture, causeways, terraces, residential groups, and reservoirs. And we can also look at how the site itself is organized.
Yeah, using the public architecture, we can look at how the ancient Maya at Caracol distributed their different plazas and other formal architecture that would have provided services across the city as a whole, and where those service access would have been for the average residents of Caracol. Looking at the whole landscape, about half of the, well, more than half of the people within Caracol would have been within a 25-minute walk of their closest formal plaza, where they would have done any sort of social gatherings, performances, participated in market exchange, gone to a ball game. And if you look at where Caracol is situated on the landscape of the Vaca Plateau, it's in this plateau between the Mopan and Macal rivers, and it's extracting resources along the eastern end, and it's able to export them along this east-west trade route that it's spanning.
Now, one of the other things that we've been able to show using the LiDAR is how intensively modified the landscape is for the ancient Maya beneath this forest canopy. This is not a pristine forest whatsoever. The entire landscape was dug up and moved around. We started to get a hint of that in the 1990s when we were intensively focusing on terracing. However, we could only map small samples. In this case, this is a square kilometer sample about 5 kilometers out, showing the relationship between agricultural terraces and the settlement. And digging those terraces shows that they actually modified the landscape all the way down to bedrock. Most of our colleagues did not really think there was that many terraces at Caracol. The LiDAR, this is just a LiDAR image from anywhere on the site. This is the Puchituk terminus in the middle, but you can see the house mound groups, and all of the lines on the hills and in the valleys represent agricultural terraces. There's over 160 square kilometers of agricultural terraces within the city of Caracol, surrounding most of the settlement.
And those terraces were designed to manipulate the flow of water across the landscape. Again, Caracol spanning between 2 rivers, but it doesn't have a potable natural body of water. So the Maya are relying on precipitation. These terraces being manipulated down to bedrock, when they're rebuilt, they're able to guide the flow of water so that it zigzags as it goes down the terraces, which further reduces erosion, and it decreases the speed of flowing water to help increase the penetration of water into the soil. At the same time, the other major source of drinking water would have been the reservoirs that the ancient Maya built. Initial models viewed a lot of these reservoirs as being elite controlled, located in the downtowns or in district centers. But if you look at their distribution across the landscape at Caracol, you can see that it would have been very difficult or impossible for the elite to control all of these reservoirs. And there's quite a high degree of residential autonomy over water management.
One of our foci for our archaeological excavations has been on the residential, the residential groups at Caracol. We spent the first portion of the project and continue today to continue to excavate these. We've got substantial information on how these houses were constructed, how they were used. What the LiDAR adds to that tremendously. It's because of the LiDAR, Arlen. Thank you. It's because of the LiDAR that we can actually get a sense of how many residential groups there were at Caracol and where they were located. Each of these dots is a residential plazuela group, so there are multiple houses incorporated. Our estimate here is more than 7,700 of these residences were located within the city of Caracol. Each of those dots, you can see the squiggly lines are the causeways. Arlen mentioned before that it was only with the LiDAR that we were able to start to see the boundaries of Caracol, the city. I think you can see from this image here that while we were able to see a little bit of decline in the population, we have not yet found the boundaries of ancient Caracol.
And at the same time, instead of just being points on a map, these different shapefiles have the areas, and we can calculate the volumes for the plazuelas. And using that, we can investigate things of modern interest like inequality in the city for the final period of occupation. And you can note that the area and volumetric Gini indices are quite different. Looking at different measures of inequality, you can get different results with the same data sets. But you can investigate other aspects like density. So in this map, it's the older density map of Caracol looking at elevated groups. And then this has been updated with those 7,700 points using kernel density. And it gives you an idea that instead of concentric rings of density around these nodes, that there's sort of a smear of population that goes east-west, and it's located within and among the different districts and nodes of formal architecture and urban services. And then if we zoom in again, we can also look at other scales below this sort of district service level and investigate neighborhoods at Caracol with those neighborhood boundaries reconstructed using the LiDAR data. And then we can use those neighborhood units as a lens to test against archaeological data of those households that have been excavated. And then zooming out, we can see that the LiDAR is, in this part, SRTM and other remote sensing technologies are helping us identify differences between Maya cities, where Tikal has a dense, concentrated urban form, and Caracol's invested more in a sprawling urban infrastructure.
When we show the images of Caracol, it sometimes seems a little bit abstract. It's useful to compare Caracol to some contemporary places that we might be aware of. So Caracol on the right, and on the left is Washington, D.C., the District of Columbia, at the same scale. And you can see that Caracol, the city, and the District of Columbia are actually about the same size. They are a little bit different, though, in terms of density, with DC being about 7 times as dense as Caracol. Arlen started by saying how it took us a little bit to get the funding for Caracol, and that initially it was seen as something nice to have. It's now something that everyone needs to have, at least to answer certain kinds of questions. So from 2009, when we were the only project to undertake LiDAR in Mesoamerica, you can see up to 2016 on this map, all the different sites and projects that acquired LiDAR to help them answer important questions about ancient Mesoamerica. But since then, there have been additional projects to gain LiDAR to help us understand what the ancient landscape looked like. But even on this diagram here that was created by Marcello Canuto, you can see that there's a lot more space that we have yet to explore to fully understand what ancient population history looked like in the Maya area. So our task was to talk about how LiDAR has changed the way we see Caracol and the way any of us might see the Maya. It's through the scale that we are able to apply because of LiDAR and the incredible detail in combination with the archaeological research, at least at Caracol, that had already taken place. We were able to make some really striking interpretations about the ancient Maya. There's some things that we thought we knew before, the LiDAR helped us prove. There are other things that were really unknown to us that we were able to explore because of the LiDAR. And there's still many more research projects to go. We now are positive that there were large cities with urban planning like Caracol in the Maya area, and how important that intensive agriculture was to them, that it was not in small plots, but it was citywide, that water resources were not solely located in places of elite control, but were distributed across the countryside, and that the entire landscape of places like Caracol was anthropogenic, it was modified. Importantly, it also helps us see how large not only the cities were, but the population numbers and the density and the complexity of these enterprises in the ancient past. Caracol has shown us how important LiDAR can be to understand one place. It has made a huge difference in our interpretations today, and there's much more that we intend to do. Thank you. And of course, like all here, we couldn't have done this research without the support of institutions, colleagues, foundations.
Thank you all so much. That was awesome. And again, thank you for, or maybe I shouldn't thank you, I don't know, for making me aware of LiDAR and you know, fundamentally changing the path of my career, I guess. Me and many others, I think. To keep us in the interest of keeping us on time, let's turn immediately to Takeshi Inomata's presentation. Archaeological investigation through high resolution and low resolution LiDAR in Mexico.
Thank you, Chris. I'd like to thank Chris for the kind invitation to this conference. And it is honor to follow Arlen and Diane, as Chris said, who are the pioneers of the LiDAR studies. In this talk, I'd like to talk about the combination of high-resolution LiDAR, that's a kind of the LiDAR that Arlen, Diane, and Adrian are using, and low-resolution LiDAR. So this is the area we are working. So we are covering this large area of 85,000 square kilometers. Diane showed the same map of this previous coverage of LiDAR in Maya area. Compared to those, you can see how large this area is. It's not quite the Amazonian basin, but it still gives us a pretty wide coverage. This LiDAR coverage was done by Mexican government, INEGI, Instituto de Estadística y Geografía, and then they make this data available to public. So that's what we used. But again, this is a low resolution LiDAR, so we are missing actually lots of things. But at the same time, this gives us a major advantage of this wide coverage, and then it can you can find many sites. So with this, so previous LiDAR focused on single sites or single region, but with this coverage, we can really do truly interregional study. In this case, covering part of Maya-Lowland and their almost entire Gulf Coast, Olmec heartland. So this is the area. So the INEGI low resolution LiDAR covers the entire area continuously. But we also did high resolution LiDAR to check accuracy of what we are finding in low resolution LiDAR. So this is our high resolution LiDAR. And then also we use this G-Light LiDAR, which is the high resolution LiDAR that was done by NASA. So we should pay attention to the efficiency of this LiDAR set, difference of LiDAR set. So this is NCOM, is the one many of us are using, a high resolution LiDAR. First, we did it in Ceibal, that's in the rainforest. In rainforest, ground density may be less than 0.6 or so. But in this part of Mexico, it's pretty much deforested. There are patches of secondary forest. So here, high resolution LiDAR gives you a density, a ground point density of 10 point something. G-Light a little bit lower. INEGI LiDAR, if you see, pulse density is much lower. Ground return density is 0.03, which is much lower. So this data set is pretty much underused by archaeologists because many people thought this is not really useful for archaeological purposes. But I would like to show that actually it can be pretty useful. I should also mention that our colleague at the NCOM, Juan Carlos Fernandez, reprocessed INEGI LiDAR data, crowd point, and then created higher resolution DM raster, which is 2 meter resolution. Original INEGI version was 5 meter resolution. This also helped. So we can even improve those low resolution crowd point data to get the better result. So this is the area. Originally, we didn't know much about the area. There were a number of previous studies, partly because it's pretty open. Our original focus was this site, El Tiradero, that's close to the San Pedro River. We started to work in this area 2017. We did a LiDAR in 2017, that's a high resolution LiDAR, and then another high resolution LiDAR in 2019. So this is the original high resolution LiDAR we did, focusing on this site of El Tiradero. But the interesting thing was what we found in this northern edge of this LiDAR. You can see there's some huge landscape modification. So this is the aerial view of the area. You can see there are lots of those ponds. We wondered about it. And in the back, this is the part that was covered by LiDAR, just this part. So we walked around looking at this LiDAR, but it's still, you cannot quite get the entire picture of the site because it's so huge. And then we noticed that actually INEGI, this Mexican government, covered the entire area. So we checked this publicly available data. Then you can see now it has actually pretty nicely made rectangular shape, obviously artificial construction. Then we did the high resolution LiDAR of the entire area. So now you can see pretty nice construction, which is huge, 1.4 kilometers long. And then a series of causeways and the reservoirs. And then here you have another big construction. Actually, this turned out to be largest and the oldest monumental construction in the entire Maya history in terms of construction volume. Remarkable thing is that, again, nobody knew about this huge site because it's so hard to recognize this horizontally large site when you are on the ground level. Again, this is the view, or ground level view. We are on the causeway, Western Causeway. This is the large platform, or we call it plateau. It just looks like a natural landscape if you are on the ground. So that's why people really didn't pay attention to this site. When you compare the low resolution LiDAR and the high resolution LiDAR, you can see the difference. And this part in this low resolution LiDAR, this part is pretty open. Then you can see pretty well even in this low resolution LiDAR, including those causeways. But this part is covered by secondary forest. Then really this LiDAR, low resolution LiDAR, doesn't penetrate well, and then it doesn't show the structure very well. So we have to pay attention to these limitations. So we analyzed this entire area of 85,000 square kilometers. And then this is the main result. Basically, we find almost 500 archaeological sites dating to the same period as Agua de Phoenix. Most of them have similar rectangular shape. And then so we can see there's a really the connection between this Western Maya lowland and then this Olmec area, and then shared similar architectural pattern. Some sites were known previously, but nobody really noticed those rectangular shape. Again, it's very difficult to recognize. Just if we look at another example, this is a site of Carmelita. It's much smaller than Agua de Phoenix, but it has this perfect rectangular shape. This site was known, just located next to modern town. Archaeologists knew about this central mound, but did not notice this rectangular shape because it's so subtle, even in this open area. So interesting thing is that we can get a new find for those intensively studied area or intensively studied site. One example is this Olmec capital of San Lorenzo, which has been very intensely studied, starting with the research by Michael Coe and Deal, and then currently it's studied by Ann Cyphers. Of course, this site is famous for this huge colossal head sculpture. It's a little bit older, even older than Agua de Phoenix. So this is really the excellent map of San Lorenzo. It's again a huge plateau, but shape looks like a sort of amorphous shape. And then there has been lots of debate what this shape represents. Then, if you see the LiDAR of this San Lorenzo, this is the reprocessed INEGI LiDAR data reprocessed by Juan Carlos Fernandez. So traditional map sort of these edge platforms, 20 of them. But they were not really quite recognized as edge platform, and then just drawn in those amorphous shape. But if you see the LiDAR data, even this low resolution LiDAR, you can see this sharp edge of this edge platform. And then you can see each of this edge platform has rectangular shape. And then this rectangular shape define rectangular space in the middle. Actually, so San Lorenzo was very similar to Agua de Phoenix. So this is similar to what happened at Agua de Phoenix. When you are on the ground level, even in this intensively studied area, it's very hard to recognize those shapes, horizontally large shape, when you are on ground. Even while you are using high precision equipment like a total station, even though you use total station, still you are representing your subjective interpretation of landscape. Then it's depicted in those amorphous shape. But in LiDAR, you can see this really nice rectangular shape. But so even this low resolution LiDAR give us a very important insight, but we have to be aware of what we are missing. So this is the overall accuracy of detection in Inehi LiDAR data of archaeological site compared to high resolution LiDAR that we have. When we look at those rectangular complex of larger one, which has length more than 400 meters, we can get almost 90% of them because it's pretty areas relatively open. But the smaller version of rectangle, we get about the half. And the major center, we get many of them, but minor center, we miss some number. When we talk about the smaller mound group, those are residential group, we get about 20%. We are missing lots of them. So we have to think about those limitations too. So in summary, so what's really we learned through this experience is that actually recognizing horizontally extensive structures are very difficult to really see when you are on ground level, even in a very intensively studied area. So those things comes out very nicely, even in low resolution LiDAR. And then that really transforms our understanding of past landscape. And then so this means that even in very well-studied area or well-populated area in modern days, you may get very important findings through the use of LiDAR. Even in this case, even using low resolution LiDAR. So broad area survey has a definite advantage. Now we can get really a truly inter-regional perspective, which in this case became possible because of this publicly available low resolution LiDAR. But I'm not particularly advocating for the use of low resolution LiDAR either. We have to be really aware of that limitation. But as I said, Inehi LiDAR is currently very underutilized by archaeologists. And if you have available low resolution LiDAR, you should definitely check low resolution LiDAR and then check what you can get. But that doesn't mean that that's the end of the research. We really have to eventually get the high resolution LiDAR. And then we have to check what we are missing. And then we have to get better picture through a high resolution LiDAR. Of course, still the cost is the problem. But in our case, we analyze this low resolution LiDAR first. Then we can really strategically select the area for high resolution LiDAR coverage. So in this way, you can build your research strategy very efficiently using these publicly available and low resolution LiDAR. Thank you very much.
Thank you so much, Takeshi. That was super interesting. And I think this approach has to be a key component of building a scalable Airborne LiDAR program, which is something that we've been talking a lot about. Of course, with Juan Carlos is one of the people that has been involved in that discussion. So thank you so much.
Sure, thank you.
And next, I'd like to introduce Keith Prufer, who's going to talk about LiDAR archaeology and human adaptations in the neotropics.
So I'm going to talk a little bit about some of the LiDAR work we've been doing in southern Belize. We were, soon after Arlen and Diane at Curator, we obtained our first LiDAR data set, which was flown by NCALM in 2011. And more recently, we've obtained a second LiDAR data set, both from the area of southern Belize, which is a kind of a, was until a number of years ago, relatively understudied region. And we're primarily interested in settlements, in human adaptations in the landscape, and being able to flesh out better ways to look at demography, to look at landscape use, and to look at inequality. And Amy Thompson's going to talk about more about the work we've been doing with inequality in the next presentation with Gary. And I'm going to talk a little bit about kind of what we've been doing and what we've learned so far. So southern Belize is this region here. You can see from the inset, it's located in southern Belize, couched between the Gulf of Honduras and southeastern Guatemala, northern Honduras. It's definitely geographically peripheral to the rest of the Maya lowlands and tends to be scaled slightly smaller, but still has a large number of sites you can see here indicated. Each one of these is a small capital that was located in southern Belize. Most of them are late classic, and our two LiDAR sets are also shown here. And I'm going to start with talking about the one here at Ushbenka, where we had conducted archaeological investigations, including a large settlement survey for a number of years before we flew the LiDAR. And the second one is that brown area to the north, which is in the Bladen Reserve, and I'll get to that second. So we first flew the LiDAR at Ushbenka. It was pretty eye-opening and mind-blowing in a lot of ways, much as I'm sure it was for the people, Arlen and Diane, when they first flew their LiDAR at Curator, as to what we could see. In the top left, you can see a bare earth model showing the architecture that revealed itself. Most of this architecture we already knew about, of course, because it's in this site core and it's within a couple of 100 meters of the road, but we'd never actually seen the visualization or the scale to which landscape modifications were part of the whole program of investment in this landscape starting rather early on. And these other two visualizations show the polygons of the architecture, core architecture drawn over top of those landscape modifications in the top right on the bare earth model, and on the bottom on the total cloud point. And what you can see there is you can see a lot of the disturbance from modern agricultural use of the landscape from the village of Santa Cruz, which is located right there. By the time we had this LiDAR flown, we'd already spent several years surveying hinterlands, chopping through this kind of low vegetation, the remains of cornfields that have been grown in the past few years, and a lot of kind of nasty conditions to survey in, not made any easier by the extremely hilly terrain and the need practically to have guides to show us where every hilltop was. But on the tops of almost all the hilltops, on the top of all the hilltops, we found settlements that were related to the ancient site, and began a program of excavation and chronology building for those. And one of the things we found was that almost all of the investment in modifying the core areas of the built environment to accommodate architecture were wound up by 400 AD. So most of the investment here was during the early classic, and much of the settlement expansion was in the late classic after those initial work. We also were kind of enamored by the fact that we could visualize the small Maya village of Santa Cruz with a population then of about 450 people, and really begin to see the way that the settlements were laid out in a modern village in contrast to those of the ancient city in their midst. And you can see some of the settlements we surveyed here in red, which were in the village itself. We didn't really get to survey much of what's in the village because it would have been an invasion of people's privacy to have us in their backyards, which were quite small, looking for architecture. And many of the houses in this village were actually built on top of dry, elevated areas that housed platforms in the past. We were really able to begin to get a look at how landscape modification appears spatially and some ideas of how it might have appeared in the past. We were initially interested in trying to resolve some issues that arose from the LiDAR, one of which was that a lot of the architecture in the settlements that we had found in surveys were hardly detectable at all on the ground in the LiDAR. And this is a combination of 3 different factors, one of which is many of them were quite small. In other words, they were ephemeral. The remains of the platforms were between 50 centimeters and a meter tall, and they were confounded by issue number 2, which was that there's a lot of very low-lying dense vegetation because of the agricultural nature of the village itself, where they are literally every year going out and cutting and burning areas that were part of the ancient city of Ushbenka, and then letting them recover for a number of years in the fallow period for slash and burn. And we found that using different types of visualizations definitely began to help us enhance our view of the landscape and begin to tease out these small settlements. Because we were really interested in trying to reconstruct the totality of demography, it made sense for us to really not ignore the small settlements, the more ephemeral settlements that probably characterized the majority of what was an agrarian farming community that became a modest-sized polity in the classic period. So we were interested in how we could do this best. One of the major things we found that helped us with this was being able to recognize not just the architecture itself, but the mild landscape modifications that accompanied each house. Each hilltop house began as a hilltop, and then people began to construct on top of it, oftentimes leveling the hill itself. We're in an area in southern Belize where it's not limestone as a bedrock or substrate, but it's actually sandstone and mudstone, and with a fire-hardened hardwood stick, you can actually break the bedrock down and begin to shape the hilltop itself. We found that these hilltops were where they had serious investment in them, particularly houses that were occupied for likely more than a generation, showed more investment in the modification of their hilltops and made them more visually available to us using LiDAR. And in the end, we were able to publish several articles discussing how we were able to expand our ability to use LiDAR to actually estimate the number of settlements within the landscape of itself. But it did take kind of walking through it very carefully and looking at things such as the slope, the amount of vegetation cover on top of it, the amount of modification, and then a lot of ground checking to make sure that there were actually architecture was actually on top of these modifications that we saw. The second thing we were kind of looking at in this area was understanding fallow period subsistence and demography in the ancient city by using the historical ecology of the people living in Santa Cruz today. This image really shows the extent of modern technology that's been applied to agriculture as of about 2011 in the village, and that consists of that modern technology consists of a machete and a pair of rubber boots. Those are the only real changes that have occurred in maize farming since the classic period. So it offers us an opportunity to begin to explore how many people a landscape can sustain within this concept of kind of, maize as a staple grain supplemented by other foods being the basis of the diet in the past. We also recognize that certainly the landscape, the use of the landscape agriculturally was probably as highly varied in the past as it is today. This image here shows the presence of tree orchards and milpas in various stages of fallow from a location just a couple kilometers from Santa Cruz Village, near to the village of San Jose and Criquehute. And you can see that using a combination of LiDAR and satellite imagery from a GlobalEye satellite image stereo set that we obtained in 2010, we were able to track the ages of milpas from 2010 through the satellite imagery to 2011, where you see a fresh milpa here on the left. And we were able to backwalk that using the height of the recovering vegetation to actually get 4 and sometimes 5 years of recovery of the landscape and begin to look at what the fallow period itself looked like. So we use this LiDAR in combination with satellite imagery to estimate agricultural potential for the landscape. And here you can see a couple of pictures of farms, one an active farm and one in about its second year of fallow. And we were also able to calculate fallow period lengths, which is the critical factor limiting productivity or the amount of corn you can grow in a landscape using slash and burn technologies. In the end, we were able to find out quite a bit about these landscapes. You can see at the top here is a image showing the 2010 cleared farms derived from the satellite imagery and the 2011. And you can see just in those 2 years, a huge chunk of the landscape is in production for different food crops. So we went through most of the landscape and delimited these and tried our best to ascertain through vegetation height the use of them. And what we found was that indeed most of the landscape was in use most of the time. Here's just a couple images showing how this vegetation recovery looks like in profiles that were generated fairly early on using Q-coherent software. You can see this is a fresh clearing in the LiDAR from 2011. Here's a 29 clearing. You can see some trees are beginning to come back and the vegetation has increased in height. And here is a 2018 clearing. And this one, the vegetation is back to about 3 meters, because in this area, we do get about 1 meter of vegetation growth per year with the very high rainfall we get. So the results kind of looked like this mosaic. We found that in Santa Cruz Village, the fallow period is rarely longer than 5 years. So most fallow periods are between 1 and 4 years for most areas of the landscape. We have to assume that part of the landscape must have been in the past also in orchards or other types of tree crops. So slash and burn or shifting agriculture would have only been part of it. This is far less than the 15 to 20 years that's assumed for fallows in the southern lowlands, and it just shows us a lot of variability. And we attribute most of this to the substrate of the bedrock, which has relatively fast petagenesis. So combined with yield data and net caloric returns from corn, we can begin to develop proxies for population estimates. And our data suggests that productivity potential exceeded populations for the classic period, which probably allowed people to do other things like use some land to farm cacao or other types of products that might have been for an export market, which I think Amy will touch on in her talk. We combined this with several years of data that were collected by a PhD student, Brendan Culleton, at the University of Oregon. He's now at Penn State University, looking at productivity on the particular landscape in terms of the amount of corn that can be produced each year using the two very, very different types of farming techniques of slash and burn and mata hambre to be able to get at what caloric potential the landscape had in terms of per acre. And we came up with some relatively interesting observations depending upon the number of plantings of corn per acre, between 4,000 and 7,000 plantings. This is not individual plants, but it's individual holes into which 2 or 3 corn seeds are thrown, and then the fallow population levels of fallow based on basic caloric types of needs. And we found that if people farmed within 3 kilometers of the site core itself, we could have had a maximum population probably around 4,100. But if we bump that out to 4 kilometers from the site core, it looks like we probably had a population limit of around 6,800 people during its peak use in the end of the classic period. So I'll move really quickly now then up to where our new LiDAR data set is, which we just got in 2019. We've not been able to ground truth it yet because of COVID, and we're going to be expanding this data set further in the next couple of years. This area that we're looking at here is in the Bladen Nature Reserve. It is a very, very difficult to reach. It's about 35 kilometers from the nearest place you can get a donkey, let alone a vehicle. And so to get in there requires being on foot or being in a helicopter. And once you're in there, it's very rugged terrain, very steep karstic mountains, punctuated by these valleys, these alluvial valleys. And this is 2 valleys at the very top of the Bladen itself. And we have a number of interesting sites here. First of all, we've been working for the last 2 years at 2 rock shelters in this area, which show continuous occupation in the region from 12,500 years ago to 1,000 years ago. And so these are not really relevant to this, but they're one of the things that drives us here, as well as 2 surface sites, Mukle Balsul and Exshush, and large remnants of cacao groves that are present throughout this area that are remnants that have been growing freely since the classic period without any human intervention. This area has never been logged, has never been subject to modern historic settlements, so it is kind of unique. This landscape is very kind of interesting in that all of the tree cover itself is what has recovered since the classic period. And you can see the ruggedness of this here. This is a 1.5 kilometer longitudinal stretch. And you can see the rock shelter here at the edge of these 250-foot tall mountains, and then the valley floor below. One of the sites, Mukle Bal Sul, which was occupied in the classic period, is probably the largest site in the region. It has a plaza. It's the largest site in southern Belize, certainly not the largest in the Maya lowlands. It has this wonderful large plaza here. This has never been excavated, particularly except for a little bit in the 1990s. It sits right above this giant sinkhole, which I excavated in 1999. We didn't find much down there, but it's hard to imagine it's a coincidence that this large ridgetop site was built right over this giant sinkhole and must have had some importance. And you can see that quite clearly in the LiDAR itself. The second site is Ekshush, which is located in the Ekshush Valley, which is a large alluvial valley. You can see it here surrounded by settlements and the hand-drawn maps from the 1990s, which proved to be pretty good, and the full expanse of the valley floor below, all of which would have been in production. And every 50 or so meters throughout this entire valley, there are also cacao trees growing, kind of wild, malnourished, low producing, but still they are domesticated cacao trees that have had the genomics work done on them at the University of the West Indies. Our coming up project is going to try to look at the distribution of the plants.
We're out of time, Keith. So
this is my last slide. Yeah, we're just going to be looking at the distribution of plants and palms in this area over the last 10,000 years to begin to try to reconstruct that landscape. So thank you very much.
thank you so much for that presentation, Keith. It was really fascinating. And thanks for agreeing to be part of the Congress. And we'd like to move to our final talk in this session, which is by Amy Thompson and Gary Feinman, Integrated Perspectives on Multiscalar Classic Maya Inequality.
Thank you, Chris, for inviting us to be a part of this session and part of the Earth Archive Congress. Our paper is titled Integrative Perspectives on Multiscalar Classic Maya Inequality. My name is Dr. Amy Thompson, and my co-author is Dr. Gary Feinman. First, I'd like to take a moment to acknowledge the traditional homelands that we're situated on here in the United States, and in particular in the Chicago, Illinois area, where the Field Museum is located, as well as the traditional homelands of the Mopan, Kikchi, and historic Moche-Chol Maya in southern Belize, where much of this research takes place. So our main research goals of this talk, which I will try to keep to less than 10 minutes since we're running a little behind, is to expand on the use of LiDAR data for settlement identification, which has been used extensively throughout the Maya region. And so to use LiDAR to first assess the manifestations of inequality at political centers, as well as within their intra-urban communities in things like neighborhoods and districts at two classic Maya polities located in southern Belize, and then compare our findings that we calculated using LiDAR data at multiple scales to other settlement survey data at the polity level, subregion, and larger Maya region. So first, what is inequality? It's something that we engage with every day. The way that we're going to be looking at inequality is through house size. And this is something that we experience all the time when you're driving around or walking through your city or a new city. You may see houses and you can have some impressions of the type of wealth that may be invested into that architecture. So just two quick examples is the variation in a mansion in terms of just the physical size and amount of square footage, for example, per person, compared to small apartment complexes. And this is an example of apartment complexes in the Pilsen neighborhood of Chicago, where I was living. So you can see that these are much smaller, much less room per person compared to a mansion. We can also then step back a little bit and look at these in terms of neighborhoods as a whole. So this is some Google Earth imagery from the Pilsen neighborhood, again, of Chicago, and another neighborhood, Hyde Park. And just looking at this, these are at the same scale. You can see some pretty distinct differences where the Pilsen houses are smaller, they're closer together, and there's a lot less green space, versus in Hyde Park, there's a lot more green space in this neighborhood. The houses are a little bit larger, and the houses are spaced apart a little bit more. So what are neighborhoods and districts? We define neighborhoods as a group of co-located residences with frequent and repeated face-to-face social interactions. So on this map here of the Chicago neighborhoods, here's Hyde Park, and Pilsen is located down in the Lower West Side neighborhood. And neighborhoods make up districts. Districts are composed of larger groupings of neighborhoods that contain district seats, which in the past would have had both administrative and high status residential functions. So in this talk, I'm going to be briefly talking about how we used LiDAR to look at wealth inequality at neighborhoods, districts, and the polity level at Ushbenka and Ishkukuwel. Let me see if I can get, oh, there's the laser, perfect. At Ushbenka and Ishkukuwel, and then we're going to jump out to the micro region of southern Belize using traditional settlement survey data from some of these other sites, and then compare that to other published Gini coefficients across the Maya region. So as Keith mentioned just a few moments ago, in 2011, the Ushbenka Archaeological Project acquired 135 square kilometers of LiDAR data, and we used this to help identify where these different household plazuelas or residential units were located across the landscape. Between the two centers of Ishkukuwel and Ushbenka, we identified more than 300 household plazuelas, almost all of which are situated on these discrete hilltops and ridgetops. So going back to that example of the differences in sizes of houses, here are some examples of sizes of classic Maya houses and what they look like today. So a larger classic Maya house in southern Belize is this structure right here. It's about 3 meters or 10 feet tall, and it would have required significantly more labor and resources to construct than some of these much smaller houses like this one here. This household platform is just a simple line of stones that would have had a perishable superstructure situated on top. These are classic or modern Maya houses in the communities that we work with in southern Belize, but they provide a nice example of the type of perishable superstructures that we would have seen on these platforms in the past. So we can use the anthropogenically modified hilltops that Keith just talked about that are visible on this LiDAR data in order to calculate the house size at these different houses across the landscape. So here's a hillshade model, and you can kind of see where these plazas are and house mounds, but on the slope model here, you can really nicely see these flattened hilltops and spaces that would have been used for day-to-day activities. In this profile schematic here, you can see where the natural hill is, and that these edges of the hill would have been built up to create a larger living space for these classic Maya houses to be located on. So using that premise, we use the LiDAR data to calculate or to create the LiDAR DEM to create a TIN to calculate the volume of surveyed households. We're primarily focusing on the entire plazuela group, as this is more indicative of the total labor used to create the household area, but aligned with traditional archaeological survey, we often also have to use the total of all structures within your plazuela group or your residential group. So we can use house size in order to evaluate inequality using something called the Gini coefficient. The Gini coefficient is a numeric representation for the area underneath the Lorenz curve, and Adrian Chase showed an image of this earlier. And the Lorenz curve is a visual representation of the portion of cumulative sums. And for a Gini coefficient of 0 equals perfect equality, and a Gini coefficient of 1 equals perfect inequality. So in this example of 15 houses that are exactly the same size, the Gini coefficient is 0, and the Lorenz curve is actually underneath this line of equality. And an example of extremely high inequality, 14 houses are the same size with one much larger house, and you can see the Lorenz curve here, and the area underneath it is 0.92, so very high inequality. And we also, this exists along a spectrum from 0 to 1, so here are some examples of what different house sizes may look like compared to their Gini coefficients. And I would like to give a shout out to Adrian Chase for providing the Excel spreadsheet to create these Lorenz curves. Thank you. So we use the LiDAR DEMs in our settlement survey data in order to calculate house size, and then use that to calculate the Gini coefficient to look at wealth inequality first at neighborhoods, then districts, then polities in southern Belize, and then the greater Maya region. For the neighborhood and district data, this was recently published in an open access article in PLOS One titled Assessing Classic Maya Multiscalar Household Inequality in Southern Belize. I welcome you to go online and check it out. So real quick, some of the main findings at the neighborhood level is that there's high degrees of inequality in neighborhoods, meaning that there are very large houses and very small houses in the same neighborhood. But likewise, there are neighborhoods that have low inequality, meaning that all houses are more or less the same size. And finally, we found that there was high inequality even outside of neighborhoods, where the houses that are not located in neighborhoods varied greatly in their size. Jumping out to the district level, this map has the volume of the different house mounts here, which are identified by the variations in size and color of the points, where blue and green are larger houses and orange and red are smaller houses. And a few of the key takeaways are that larger households are surrounded by smaller households, and that this happens both within neighborhoods and districts. That there's high inequality within districts, such as District 1 in both sites, as well as high inequality in houses that are located exterior to districts, like these houses over here, where you have some fairly large houses surrounded by smaller houses. Higher inequality was present among older districts based on the chronology building, which I won't get into right now. And then we noticed that there was high degrees of inequality that seemed to be linked to trade and exchange of prestige goods. And this is based both on modeled least cost paths that pass through the site of Ushbenka and connecting Ushbenka up to Ishkukwil, as well as identifying more prestige artifacts in these districts with higher Gini coefficients. Now we're going to take a step back out to the southern Belize region. And again, Ushbenka and Ishkukwil Gini coefficients were calculated using LiDAR data, while these other sites such as Mukli-Balsul, Ekshush, etc. were calculated using traditional archaeological pedestrian survey. So a few key findings are that there's variations in wealth inequality, but generally it's fairly high. Most of them are above 0.5, with the exception of Kakruha, which is a small hamlet located down in this region. Also, that southern Belize divides into 3 distinct groups based on Gini, and this is especially noticeable in the area Gini calculation. And again, that we believe that inequality was linked to trade and the manifestations of power, and this in part was done through a social network analysis of least cost paths. And then stepping out one more time to the greater Maya region, if you'll recall, our Gini coefficients in southern Belize were fairly high, around a 0.5. And this is similar to the sorts of inequality that we're seeing in published Gini coefficients for house size across the Maya region. I would like to note that using the Gini coefficient is not the only way for archaeologists to identify wealth inequality in the past, but it does provide one of proxies that we can use in order to understand past human behaviors, and especially with the use of LiDAR data. So in conclusion, we use LiDAR data to examine wealth inequality and house size differentials at several scales for classic Maya settlements. These results generally align with what others did for sites where we have more traditional settlement survey data, and that these peripheral sites had high degrees of inequality, but that site segments were not uniform. We saw differences in wealth inequality within neighborhoods and districts at Ushbenka and Ishkukwil based on the LiDAR data, and that their access to trade routes and longevity of occupation also seemed to correlate with greater degrees of wealth inequality. So thank you so much. We're happy to answer any questions, and thank you to all the funders, and once again, thank you to Chris for inviting us to be a part of this session.
Thank you, Amy and Gary, for that great paper. And of course, we're out of time, so it's time for questions. But there is a speaker lounge where you can go and people can catch you and ask you some questions. And I should say that, you know, people have been WhatsApping me on the phone while the presentations are going on. And a lot of the Amazonian folks are really blown away by all of this. Many of them are not, you know, really that familiar with the research that's happening, with this kind of research that's happening. And so by you know, giving these talks, it really provides some examples of what the possibilities are and what the current state of knowledge is for